Welcome you all for the presentation. I am Dr. Sangeeta DM, Associate Professor, Department of Civil Engineering, AG Institute of Engineering and Technology, Mangalore. Today we will be discussing on analysis of determinate structures 18 CV42. This is the VTU syllabus. In that module 3, deflection of beams. In that again we have several methods. Maculays method will be the session for the day. So this is module 3 part 1 where we will be discussing about Maculays method. First of all, before getting into the content, what is deflection? What is deflection? So if there is a beam which is subjected to different loads, it may be a point load or a UDL, a beam which is subjected to loads undergoes deformation. That deformation can be deflection or rotation. So here it is displaced from its original position and that is known as deflection. Again here this is the straight is the initial position which is displaced to its, so that is known as deflection. For example, here there are two different types of beams. One is propped cantilever. Propped cantilever means one end is fixed, other end is simply support, and the other one is one end is hinged, the other end is roller, and the third one is free end. So it is a continuous beam. So in this case, how the deflection happens? So in the first figure there is a point load and support B is fixed. Support B is fixed. So when the support is fixed, there cannot undergo any deformation. It is not allowed to move. It is totally restrained. When support A is hinged, it cannot move, but it can induce rotations in it. So here at that point moment is restricted, but rotation can happen. So at the point of load there is deflection. Similarly, in case of continuous beam, there is a point load in the cantilever portion also. Let's see how the deformation occurs. See here, due to point load there is a bending. At the supports it is 0, and as the free end there it can bend. So due to the loading it is maximum. So based on the deformation patterns, we have to establish the boundary conditions at the supports. They are the guidelines for solving our equations. Whatever the equation we get, it has to be solved using these guidelines. What are the guidelines? These are the equations which guides us for that. Okay, what are those boundary conditions? See here, support B is fixed. Support B is fixed. So whenever it is fixed, theta B and delta B are the two terms I am writing. Theta B in the sense rotation, delta B means deflection. Theta B is rotation, delta is deflection. Theta is rotation, delta is deflection. Got it? So whenever something is fixed, it can neither rotate nor deflect. So what is the boundary condition? Theta B 0, delta B 0. But what about at support A? At support A it is hinged. Hinged means it can rotate, but it is restrained against horizontal and vertical moment. Movement about or motion about horizontal and vertical directions. So at A it cannot deflect. It cannot deflect, but it can rotate. So here theta A is not 0, delta A is 0. Delta A is 0. Got it? Similarly, with that concept, if we proceed for figure 2, at support A there is a hinge. Hinge can only rotate, not can deflect. So when it cannot rotate, theta A is 0. And deflection, is it possible? No. same here, whatever it has been done. So, delta A is 0. At support B, again same thing, roller, intermediate support, deflection is not possible, but rotation is possible. Rotation means, see here, that is the theta. This is, got it? So, theta B is not 0, whereas delta B is 0. At C, so both deflection and rotation can happen. It can deflect, again it can rotate, because it is free end, which is not restrained in any of the directions. When something is not restrained, then all the parameters comes. H, V, Z, M. So, H and V together I will call it as a force. So, whenever force comes, then delta comes. Whenever M comes, theta comes. Okay. So, with that condition if you consider, then the support conditions, it is very clear and easy for you to remember. So, with that concept I would like to recollect or refresh the things for you in this. Whenever support is fixed, all three things is 0, sigma H 0, V 0, M 0. So, theta B 0, delta B 0. Okay. Whenever it is hinge, H and V 0, where there exist, H and V exist, but M cannot, correct? It is restrained against horizontal, but it can rotate, hinge. Therefore, theta A exists, rotation exists, but deflection 0. Same thing at A. H and V exist. H and V exist means theta A not 0, whereas deflection 0. So, depending upon the restraint conditions, if you compare this, you will get the answer properly. So, now I would like to define what is deflection. Structure undergoes deformation when subjected to loads. Structure undergoes deformation when subjected to loads. As a result of this, deformation, deflection and rotation occur in structures. As a result of this, deformation, deflection and rotation occur in structures. This deformation will disappear when the loads are removed, provided if the structure is in elastic limit of the material. Deformation in a structure can also occur due to the change in temperature and settlement of the supports. The last part, that is due to temperature and settlement effects, you will not be studying right now. Right now our aim is to study the deformation, deflection and rotation that is occurring, that happens because of loads. There are various methods of computing the deflections. Several methods are available. Among them, 3 are very popular. One is moment area method, conjugate beam method, double integration method and Maculays method, strain energy method, unit load method, Castigliano's theorem or Castigliano's method. So, as of now, presently we will be dealing with double integration method and Maculays method. Double integration and Maculays method. What is double integration and Maculays method? Maculays method enables us to write a single equation for bending moment for full length of the beam. Single equation of bending moment for the full length of the beam. When coupled with Euler-Bernoulli theory, we can then integrate the expression for bending moment to find the equation for deflection. So, there is a combination of two things. In Maculays method, we are going to write one single complete equation for the bending moment. For one beam, we are going to write one equation for bending moment for the full length of the beam, and that equation is coupled with Euler-Bernoulli's theorem, Euler-Bernoulli's expressions, and those expressions are integrated to arrive at the deflection. And when you are arriving at the deflection, there comes some integral constants. Those constants are evaluated using the boundary conditions which we have discussed just before. Euler-Bernoulli bending theory. Euler-Bernoulli bending theory. So, here Euler-Bernoulli bending theory, a beam is considered, the stretched or due to the action of the loading, the top fibers will be in compression, top fibers will be in compression, whereas the bottom fibers or the outer fibers will be in tension, will elongate, elongation means tension, will be compressed, shortened, whereas the middle fiber there won't be any change in length. Consider a portion of the beam of length dx between the planes AG and PH. We are particularly interested in the arbitrary fiber EF at a distance y below the neutral axis CD. Before loading, EF is the same distance as CD. After loading, it remains C dash D dash. But the length of CD, since the neutral axis to give, here is those A, B, C, D. Initial position of the beam, the same beam which you have seen here. Initial position. After the loading, it has taken a curved path. So, I have taken the curved. In that beam, I have considered one small segment CD. Under the action of loading, it has reached, become C dash and D dash. So, various positions, the distance of a fiber which I will be considering, that is E dash F dash, it is at a distance y below the neutral axis EF. dx is equal to r into d theta. The curvature length is equal to r into theta. However, after loading, E dash F dash is no longer same length as E and F, because it will elongate. Anyway, it will elongate. So, E dash F dash is not the same as EF. But the increased in length, we have E dash F dash is equal to r plus y into d theta. R is the curvature, that is from the middle neutral axis. Below that, the fiber distance is y, r plus y into d theta. See, dx is equal to r into d theta. E dash F dash is r plus y into d theta. And also, the strain in fiber EF is, strain is change in length to original length. So, change in length is E dash F dash minus EF divided by EF. EF is equal to CD. Initially, EF and CD, they were same length. What is CD? CD is dx into r into d theta. CD is because the neutral axis fiber, middle fiber will not change in the length. See here, the top fiber will shorten, the outer fiber will be longer, whereas the middle fiber there won't be any change in the length. So, CD will be is equal to r into d theta. With that concept, if we evaluate, strain is equal to y by r. Strain is y by r. Thus, epsilon is equal to y by r. Next, we will consider a specific case of the material behavior, linear elasticity, for which we know strain is equal to stress by Young's modulus of elasticity. Strain is equal to sigma by E. What is sigma? Epsilon. Epsilon is, strain is y by r. This means that by interpolation, stress is equal to E by r into y. This is the equation of a straight line, and so the stress is linearly distributed across the cross section for a linear elastic material subjected to bending. So, this is the equation for a straight line. Moving ahead, lastly, we will consider how these stresses provide resistance to the applied moment and force. How these stresses provide resistance to the applied moment and force. Consider the elemental area dA. Consider the elemental area dA. A distance y from the neutral axis as shown in the figure. The force in that area is dF is equal to sigma into A. Force is equal to stress into area. So, force if I want, I will be integrating throughout the area into dF. So, for total force is equal to force in the elemental area, that is integrated between the area. F is equal to A into sigma into dA. Since there is no applied axial force, only moment, this force must be 0. See here, there is no applied axial force, there is no axial force. So, without any axial force means it is going to rotate, and which above the neutral axis, below the neutral axis will be equal in magnitude, and that it becomes 0. Using the relationship, we have m is equal to A into y into integral of y into dF throughout the area. What is y? Y is sigma dA, that is y is sigma divided by E by R. So, using that relation, sigma is E by R into y. So, using substituting that terms, here we have E by y into E by R into y. Substituting that terms, E by R remains constant, integral of y square into dA is 1 by R, that is known as second moment of an area. The integral of area of y square into dA is nothing but second moment of an area, and it is denoted by I. So, m by EI is equal to 1 by R. So, combining all the things, here m by EI is equal to 1 by R. Here we have sigma is equal to E by R. So, bring in the relationship so that we have 3 common parameters. So, this is known as ingenious bending theory. M by I is equal to sigma by y is equal to E by R. M by I is equal to sigma by y is equal to E by R. This is the ingenious theory of the bending, and this is very, very important and golden equation. So, general deflection equation from Euler-Bernoulli theory, we have m by EA is equal to 1 by R, or 1 by R is equal to m by EI, where R is radius of curvature, m is bending moment at a point, E is Young's modulus of elasticity, and I is second moment of area at a point. We also know that dx is equal to R into d theta. So, 1 by R is equal to d theta by dx, reverse it. Further, for small displacements, d theta approximately equal to tan theta, and that tan theta is nothing but dy by dx. So, in other words, 1 by R is equal to d square y by dx square, where y is the deflection at a point and x is the distance of the point along the beam. Y is the deflection at a point and x is the distance of a point along the beam. Hence, from the fundamentals, what is 1 by R? 1 by R is nothing but m by EI, mx by EIX, in which the subscripts show that both m and EI are functions of x and so may change along the length of the beam. So, this is how the equations are modified for the Bernoulli equation. So, up to this is the derivation, which is very, very prominent. Euler-Bernoulli theory. So initially the beam is considered to be straight, and later under the action of loading the beam undergoes deformation. Due to the deformation, the top fibers will be under compression or it becomes short, whereas the outer fibers will elongate and that will be in tension. Whereas the middle fibers or the neutral axis fibers will have no change in length. The same is depicted in these two figures. When it takes a curvilinear path, let R be the radius of curvature of C dash and D dash. So accordingly, dx is equal to r into d theta, the curved length dx is equal to r into d theta. If you want to take the length of the elongated member at a distance of y from the neutral axis, that is E dash F dash, it is r plus y into d theta. Taking the strain equation, change in length to original length, strain is y by r. Strain is y by r. Also we know that stress is equal to strain, and that proportionality is replaced with the Young's modulus. So stress is equal to strain is equal to stress by Young's modulus of elasticity, and we know that strain is y by r. So bringing in both the equations, stress is equal to E by r into y. This equation for a straight line, and so stress is linearly distributed across the cross section. Now take an element, again same thing, at a distance y from the neutral axis. So we will bring in the force concept. The force in the elemental area is equal to stress into area, stress into elemental area. If we want to try find the force of the entire member, force is equal to integration of the elemental strip. So elemental strip is sigma into dA, and sigma into dA, it is stress into area, it is nothing but moment, it forms a moment. So about the neutral axis means, neutral axis is something which divides the element into two equal parts. So when you are taking moment about a neutral axis, both the ways it gets cancelled and it becomes 0. As you can see here, stress in bottom fiber, stress in top fiber, which will become 0. One will make clockwise, the other one will make anti-clockwise, and it becomes 0. Then moment is equal to integral of area, integral of y into df. What is df? Sigma into dA. Sigma is E by r into y. Substituting everything, you will end up with the equation m by e is equal to 1 by r, where the integral of area y square into dA is a second moment of area, and it is denoted capital letter I. So that is known as ingenious theory of bending. M by I is equal to sigma by y is equal to E by r. General deflection of equation is 1 by r is equal to m by I, 1 by r is equal to m by EI. So that's how the fundamental equation for finding the deflection can be brought in by correlating the things. So that is d square y by dx square is equal to mx by 1 EI. This is the equation for calculation of the bending moment, deflections from bending moments. So now moment functions for various types of loads. So before getting into the problems, I would like to just brief out how the moment functions for different types of loads are being considered. Initially in the beam, we have a point load acting at a distance A. Let the length of the beam be x. Length of the beam, not to the length of the beam, maybe the length of the span as well. So if you are taking moment about a point P into, if I am taking moment about the support, P into x minus A, P into x minus A. If I am taking moment about the other end. Similarly, if it is a UDL towards the, then it is W into L by 2, that is W L square by 2. I am not taking moment about this support, I am taking moment about the other support which I cannot see. See, x is the total length, p is here. If I am taking moment, got it? So here it is shown clearly. See, I am taking moment to the other end of the beam, not the one support shown here. If A is this distance given, the other end if I want to take, then how I am going to write my equation? W into x minus A whole square. So total length is x. A is from the support where it is starting, but I am going to take the moment about the other point. Got it? Moment about the other end of the beam. So it is like this. So load into distance. What is the distance? X minus W into L by 2. W is magnitude of the load. Distance is L is x minus A by 2. And if there is a moment m naught. So generally when there is an external moment, distance will not be considered. Distance will not be considered. So in order to write the equation where I need that x factor for further integration, so in order to do that, what I am writing is, whenever there is an external load, x minus A to the power of 0 I am writing. X minus A to the power of 0. But whenever it goes for the integration, if it is needed, that term may get in. Otherwise, for the bending moment, it is 0. Only when it comes to deflection, it will have its effect. Not in the bending moment part. So, x minus A to the power of 0. Something to the power of 0 means 1. It is equal to m naught only. Got it? So, with this concept, we will switch to some of the problems. Calculate the maximum slope and deflection of the beam shown in figure below. Take EI as 15,000 kilonewton meter square. So, what kind of beam is this? What kind of beam? One end is fixed, other end is free. It's a cantilever beam. It's a cantilever beam. So, cantilever beam means, I'll just take you back to the slides. Yes, here it was propped cantilever, one end was simply supported. But can you see this portion? So, whatever it is, whenever something is fixed, this is the boundary condition. Whenever something is free, this is the boundary condition. Whenever something is simply supported, this is the boundary condition. So, in our problem, we have one end fixed, the other end free. So, what kind of boundary conditions you may expect? What kind of boundary conditions you may expect? Theta b 0, delta b 0, theta a not 0, delta b not 0. So, at A both rotation and deflection exist, at B both will not exist. So, at A exist, at B no. So, first initially we have to write a bending moment equation. To start with the problem, we have to write a bending moment equation. So, this is a 3 meter beam span, 3 meter beam span. So, generally you have to take a section, near to the last support. After all the loads should be covered and next to the last support. So, if I am moving from A to B and I will take section at this point where I have shown in the figure, after this there is no loads, after that there is no load. So, all the parts will be considered. So, from A I will take moment about point B, I will take moment about the section, I will take moment about the section, okay, given section I will take the moment. So, if I take moment about the section 20, that is anti-clockwise. So, minus 20, 1, 2, 3, total is 3. but up to the section what is the distance? 3 minus x. 3 minus x. Again the second load is 20 and it is making anti-clockwise, so negative. Minus 20 into total distance is 2, 2 minus x. And the third load is 40, it is making anti-clockwise, so minus 40 into total distance is 1, but I am taking moment about the section, so 40 into 1 minus x. I want this distance, I want particularly this distance. Got it? So I have the bending moment equation. So mx is, be very specific in this. I'll just repeat it once again because this is the concept which will go throughout all the problems. So whenever you are going by Euler-Bernoulli equation or Maculays method, you have to consider a section such that all the loads will be considered and you will be considering it in the last span. So here AB, you have spans AC, CD and DB. So in the span CD, DB, after load D, there is nothing in that, so you are going to consider a section. So 20 into total distance is 3, 3 minus x, so I am taking moment about the section. Next, minus, because it is anti-clockwise, minus 20 into 2 minus x minus 40 into 1 minus x. Once you have bending moment equation, you have Euler-Bernoulli relation EI into d square y by dx square is equal to minus mx, is equal to minus mx. Why this minus? Based on the sign convention that we have used, is equal to minus mx. EI into d square y by dx square is equal to minus mx. So all your relation will get converted to plus. Now integrate it. EI into dy by dx, 20 into 3 minus x. So integration of 3 minus x is 3 minus x whole square by 2, and this is minus x, so minus 20 by 2, 3 minus x whole square by 2. Then plus 20 into 2 minus x, 2 minus x minus x, so it becomes minus outside, 20 by 2 into 2 minus x whole square by 2, again that minus x. So what is the integration of 1 minus x? Minus 1 minus x whole square by 2, the same I have substituted here, plus the integral constant c1. We will keep the integral constant as it is, and this we will name it as equation 1. Now at fixed end B, we have the boundary condition at x is equal to 0, dy by dx is 0. What is dy by dx? Dy by dx is tan theta, deflection and rotation. At x is 0, what is x 0? X is 0 from the support. At x is equal to 0, dy by dx is 0. Substitute for x is equal to 0, dy by dx is 0. Find out what is c1. c1 is 150. Substitute in the equation, you will get the equation for slope. Again this equation is integrated, EIY, integration of the above expression, EI into y is equal to 3 minus x whole square. What is the integration of that? Minus 3 minus x whole cube by 3. Correct? So integration means it keeps on adding. So minus means here when minus comes out, it becomes plus 10 by 3, 3 minus x whole cube. Again 2 minus x whole square, minus 2 minus x whole cube by 3. Minus 2 minus x means minus of minus become plus, plus 10 by 3 into 2 minus x whole cube. Similarly for 20 into 1 minus x whole square. Minus of minus becomes plus. So you will end up with the equation. So again you have one more constant here. In order to evaluate the constant, boundary condition. Again you have the boundary condition at x is equal to 0, y 0. At x is equal to 0, y 0. What is x 0 means? Fixed end. At fixed end, deflection 0, rotation 0. So, rotation 0 I have used. Now, substitute for y 0 at x is equal to 0, you will get what is C2. Substitute everything, all the parameters, you will get the deflection equation. We also know that in a cantilever beam, maximum slope occurs at the free end. Maximum slope occurs at the free end of the cantilever. Maximum slope occurs at the free end of the cantilever. Therefore, at x is equal to 0, maximum slope occurs at the free end of the cantilever, that is at x is equal to 0. Substitute the terms. So, you will get dy by dx max, and also maximum deflection also occurs at the free end of the cantilever. Maximum deflection occurs at the free end of the cantilever, that is at x is equal to 3. See here, when you substitute x is equal to 3, 3 minus 3, 0. 2 minus 3, the term here becomes negative. So, whenever it is negative, it is treated as 0. 1 minus 3 is negative, it is treated as 0. So, 150 into 3 by EI minus 123.34. That gives the solution. So, again the same case, y max. To be noted, here at x is not equal to 0, at x is equal to 3. Moving ahead with the next problem. Compute the deflection at midspan using Maculays method. Compute the deflection using at midspan using Maculays method. Take EI as constant. So, here the span is 5 meter, midspan means at a point 2.5 meter. You have to evaluate the deflection. Okay, fine, we will do it. What kind of beam is this? This is a simply supported beam. This is a simply supported beam. So, before starting with the problem, since the loads are not equally distributed, you have to find the support reactions. What is VA and what is VB? So, in order to do that, go back to your basics, equilibrium equations. Sigma V0, sigma M0. Sigma V0, VA plus VB is equal to 500 plus 500, 1000. Take sigma M0, take sigma MA0, moment about A as 0 at this point. 500 into 2, 500 into 4, VB into 5. So, these are making clockwise. So, positive, clockwise, positive, anti-clockwise, negative. So, minus 5 into VB is 0. So, VB is 600 and VA is 400 Newton. Bending moment expression. After knowing VA and VB, we can write the bending moment expression. So, in order to write the bending moment expression, we have to take a section. We have to take a section. So, I will take a section. I will take a section very close to support B. I will take a section very close to support B. I will take a section. However, wherever you want, you can take it. There is nothing restriction. You can take towards support A or support B. I will take a section very close to support B, and its distance from support A, I am taking it as x. I am taking it as x. From A, it is taken as x. So, writing the bending moment expression, mx is equal to VA is 400, 400 into x clockwise, and this is making anti-clockwise. So minus 500 into x minus 2, minus 500 into x minus 2, and the third one minus 500 into x minus 4, minus 500 into x minus 4. Writing the bending moment expression, I will just repeat it once again. VA is, we have taken a section in zone DB and its distance from A is x. Distance from A is x. So that is a section in zone DB. Now VA into x, that is 400 into x, because it is making clockwise positive. Next one, second one, 500 into, from A to the section distance is x. I want the distance from here to here, so it is x minus 2. Again here, from A to the section it is x. So the expression is minus 500 for anticlockwise, x minus 4. This is the bending moment expression. You have Euler-Bernoulli relation, EI into d square y by dx square is equal to minus mx. So bring in the minus relation, all your terms get negative. Minus 400x plus 500 into x minus 2 plus 500 into x minus 4. See, there is no conception that you have to use your x distance like I have done in a previous way and this way. Both are exactly similar. Only the distance you are measuring from the other supports, that's all. But one advantage in this is the negative term in the integration can be avoided when you go by this one, the negative term of the integration. See here, I will just show you. When you are integrating such an expression like this, when you are integrating such an expression, all the time you will get a minus sign. When you are integrating this, you will get a minus sign. If you take x from this end, the same x if you have taken from this side, if you have taken from this end, this could have been avoided. That's what it's being done in this problem. Got it? In order to avoid that negative term. So now again integrating EI into dy by dx minus 200x square plus 250, see here the plus remains as it is, 500 into x minus 2 whole square divided by 2. So there is no problem with the minus sign here, so you can directly integrate it, plus 500 by 2 into x minus 4 whole square divided by 2. When 500 by 2, it turns to be 250 plus 7. Again integrating, you have the second expression, EI into y is minus 200 x cube by 3 plus 250 by 3 into x minus 2 whole cube plus 250 by 3 into x minus 4 whole cube plus c1x plus c2x. Here you have the boundary conditions. What are the boundary conditions? Whenever the both ends are simply supported, at A, theta exists, deflection 0. That means y is 0 at A and at x is equal to 5 meter also y 0. So you have the two expression, at x is equal to 0 y 0, at x is equal to 5 meter y 0. But the thing is, you want C1 also you have to evaluate. How to evaluate C1? So what you can do is substitute both the boundary condition at x is equal to y 0 and x is 5. In the previous case you had the conditions which you can relate for dy by dx, that is one for rotation, one for deflection. But as this is simply supported case, you don't have the relations which you can relate for the rotation, You have the equations that can be described for the deflection. So what you can do is, the simplest thing is, you have to substitute for the deflection equation 2 times. 2 boundary condition 2 times simultaneous equations. At x is equal to y 0, So here substitute for x is equal to 0, y 0, you will evaluate what is C2. What is C2? It becomes 0. At x is equal to 5, y 0, substitute, you will get what is C1. Whenever it is for a simply supported beam, you will not have an equation for rotation. So in that, the simplified way, easiest way is to go by the 2 times calculation of the deflection at two supports. So x is 0 means at A, x is equal to 0, y 0, x is equal to 5, y 0. So the two constants are evaluated, we have the equation. Then midspan deflection, very simple. In the equation which you have, final equation whatever you get, Eyy is equal to this final equation, substitute for x is equal to 2.5 meter, you will get the maximum deflection at the midspan. Clear? You will get the maximum deflection at the midspan. And make sure always, repeatedly I am telling, if the difference is 0 or negative, if the difference between the term is negative, then that term, entire term has to be neglected. Here it is not negative, so you have to include it. Let me go for one more problem where you have the UDL, that is only for a restricted small portion. Till now in all the problems you have studied about the point loads. Now we are moving ahead for a UDL where you have some UDL is distributed for some span. So let the cross section of the beam be 200 by 600, cross section of the beam be 200 by 600. So E is given 30 GPa, but I is not given, cross section is given, and the dimensions are in mm. So BD cube by 12. In order to evaluate EI is BD cube by 12. B is 200 into 600 cube by 12. E is 30, 36 into 10 power 8, 36 GPa is 36 by 10 power 6. So EI is 108. Got it? So in all the problems EI was given here just to evaluate a simple calculation. Simply supported beam. So once the simply supported beam means you have a deflection equation for y, and you will be substituting with the boundary condition at x is equal to 0 and x is equal to L. So at x is equal to 0, y 0, at x is equal to 6, y 0. That is the boundary condition for this problem. So here you have 20 kilonewton per meter, and for our goodness it is exactly at the center. So the load gets equally distributed. So the support reactions are 20 into 4 is 80. So VA and VB are, or AY and BY are 40 kilonewton. So that's good. So reactions are evaluated. Once you evaluate the reactions, the next part is to write the bending moment equation. So whenever UDL is in the small portion, what you have to do is that load has to be extended till the end of the support. So here till point D is there, I will extend it to B, and again I will introduce a negative load which is equal in magnitude, opposite in direction, so that the topmost and the bottommost will get cancelled each other up to point D. Got it? In the zone DB, I will introduce the same magnitude in both upside and downside. So positive and negative, it means it will get nullified on its own for all the effects. See here I have extended it and introduced an load which is opposite in magnitude at the bottom layer. So now I will consider a section in zone DB. I will consider a section in zone DB, section XX. Let the distance from A to the section is x, and of this UDL it is starting from 2 meters. So 2 is x minus 2 and this is x minus 6. Got it? X minus 2, x minus 6, x minus 2, x minus 6. That is the distances of the different loads. See here properly, A is 40. So, writing the bending moment equation, about the cut section, 40 into x, UDL means W into L by 2, WL square by 2, 20 into x minus 2 whole square by 2, correct, 20 into x minus 2 whole square by 2, and this bottommost load 20 into x minus 6 whole square by 2. See here in this problem the sign convention is taken clockwise positive, anti-clockwise negative. See, this is clockwise, this is clockwise, and this is anti-clockwise. So, anti-clockwise positive is taken as, here it is written anti-clockwise is positive. So, this is the equation, and you have Euler-Bernoulli relation, EI d square y by dx square is equal to minus m. When you substitute this minus m, then you have 40x minus 20 by 2 into x minus 2 whole square plus 20 by 2 into x minus 6 whole square. That goes that side. Next, integrating the equation, EI into dy by dx is equal to 40 into x square by 2 minus 20 by 2 into x minus 2 whole cube by 3. So, 3 into 2 6 plus 20 by 6 into x minus 6 whole cube plus C1. Again integrating the second equation to get the displacement, EI into y is, integrate the equation, you get the equation EI into y, 40 by 2 into x cube minus 20 by 6 into 4, 24, x minus 2 whole power 4 plus 20 divided by 6 into 4, x minus 6 whole power 4 divided by 4, 6 into 4, that becomes 24 here. So, x minus 6 whole power 4 c theta or c1 into x plus c2. Next we have the boundary condition, as I said before, at y0 and x0 and at x0 and x8. For the first boundary condition at y0, x is 0, y0 means EI into 0, x is 0, first term get cancelled 0, 0 minus 2. So, whenever it is negative terms we should neglect it, that is what I have told here. See, it is clearly mentioned, negative terms should never be considered. So, C2 is 0. Again substituting for the second boundary condition, after solving C1 is minus 293.33. Substitute C1 and C2 in the equations, you will get a displacement equation, complete displacement equation, 40 by 6 into x cube minus 20 by 24, x minus 2 whole power 4 plus 20 by 24 x minus 6 whole power 4 minus 293.33 x. In the problem, it is asked to evaluate the maximum deflection at the center. So, maximum deflection at the center means what is y max? Y max at center is 4 meter. So, the span of the beam is 8 meter. So, at 4 meter, so substitute x is equal to 4. See here, the negative term within that brackets x minus a negative, that term should be neglected. So, here it is neglected, so that the maximum deflection is found to be minus 760 EI into y max. But EI value, you know, that is 108 into 20 cube. So, substitute that E into I, then you will get the value, and upon substituting with the proper numericals, you can end up with maximum deflection is found to be 7.04 mm, and negative sign indicates it is downward deflection. So, that is how for a UDL. Moving ahead with the last problem of this, where I would like to introduce both UDL and a point load in the case. So, determine the slope and deflection at midspan of the beam shown in figure below. Take E and I as given. So 5 meter, 2.5, 2.5, so 10 meter. At point C you are supposed to evaluate the maximum slope and deflection. Fine. To start with, as usual, use the equilibrium equation. VA plus VB is equal to 6 into 5 for UDL plus 20. So taking moment about point A, 6 into 5 into W into L by 2, 6 into 5 into 5 by 2 plus 20 into 7.5 minus VB into 10, that is equal to 0. So VB is 22.5 and VA is 27.5 kilonewton. So VB and VA are found, and just now as we solved in the previous problem, to move ahead whenever there is a partial UDL, if it is for complete span, no worry. If it is for partial span, then you have to extend it throughout the span in both the sides. From C to B you are extending UDL of same magnitude both top and bottom along with the other loads. Take a section in the last zone and its distance be x as it is mentioned here. So now I am taking moment about the section x. So first one is VA is 27.5 into x. Next UDL, W into L square, 6 into x by 2, so 6x square by 2. Next there is a point load. Next there is a UDL, that is from the bottommost zone, so that is making clockwise. This is clockwise, and due to this anti-clockwise. Okay, so anti-clockwise 6x square, and this is making clockwise 6 into x minus 5. So x is rotated to up to the section minus 5 whole square by 2, and for 20 minus 20 into x minus 5, 2.5, 7.5, x minus 7.5. Once you know M equation, next the problem is very simple. A into d square y by dx square, A into d square y by dx square, that is equal to minus mx. So minus mx is minus 27.5x, that minus it gets converted everything. So plus 3x square plus 3 into x minus 5 whole square minus 20 into x minus 7.5. So integrating the expression again, integrating the expression, A into dy by dx, x becomes x square by 2, 3 into x square is x cube by 3, 3 into x minus 5 whole square is x minus 5 whole cube by 3, 20 by 2 into x minus 7.5 whole square by 2 plus c1. Again integrate, you will have the expression here. And as the beam is simply supported at x is equal to 0, y 0, x is equal to 10 meter, y 0. That is the boundary condition. Substitute and find out what is C1, what is C2. C2 is found to be 0, C1 is 218.75. Substituting in the relation, you will have the final expression. And what you are supposed to evaluate? Maximum slope and deflection. So YC, maximum slope, is found to be at x is equal to 5 meter midspan. Find out. Substitute for x is equal to 5 in both the equations. So dy by dx means theta, y means deflection. So you will get the expression and everything in terms of EI, because EI is given there in the denominator. Divided by that and multiply by 1000, because numerator will be in meter, so you can convert it into millimeter. So that is how deflection at any point and rotation at any point can be evaluated. If you find dy by dx, then it is rotation. If you find y, then it is deflection. So this is how about Maculays method of calculations. And here we have several questions from the previous video question papers which I would like to discuss. Calculate the deflection at point C and D and maximum deflection at its location for the beam shown in figure below using Maculays method. Take EI value of 17,000 kilonewton meter square. So this is a simply supported beam with 2 point loads. Almost similar kind of problem we have discussed. And this is a question paper problem from December 2018 Jan 2019. The boundary conditions for this will be at x is equal to 0, y 0, x is equal to 6 meter, y 0. You can take a section between dB and the distance from A to the section is x. You can solve this. Second question is related to conjugate beam method, which we will be discussing in the next videos. This is a moment area method, which we will be discussing in the next videos. And here, by double integration method 3b, double integration method, determine the slope and deflection at A for the beam shown in figure below. So here this is a cantilever beam. There is a moment at the end. So once there is a moment, as I told you, you have to write the equation m naught into x minus a to the power 0. You have to write the equation like that and you have to solve this. This is a question paper problem from June-July 2019. The fourth question, or the first one, is a conjugate beam method. We will be discussing in the next videos. And the next one, 4b, is a Maculays method, which is a simply supported beam, 2-point loads. E and I values are given. So this problem is just very similar to the one which we have solved recently. So June-July 2019, we have some theory questions here. Derive moment curvature equation for deflection. Determine slope and deflection at free end of cantilever beam subjected to point load W and free end and span of L with constant EI. Use Maculays method. So instead of numericals, you have to just use this W and you have to derive that part. Method of solving will remain exactly the same way. Using conjugate beam method, so that is conjugate beam method. So we will be discussing in the next videos. So that's it for today. Here are the list of references. So the book Ready CS is a good book and is prescribed by the VTU. All these books are prescribed by VTU, and this Ready CS is available in the Google eBooks. And the link is provided here in the blue color, which is for your reference. You can go for the Google books and you can find the textbook. Also, you have Bhavikati, SS Bhavikati textbook is available. The third reference is available in the Google eBooks. You can use it as a ready reckoner for your reference. Thank you.